hydrodynamic inhibitor. It is a rough calculation. Okay. We first step, we find out how much water is in the gas stream. Okay. This chart gives you amount of water that come out with gas, amount of water that is dissolved. So we calculate the amount of water that dissolved at 8,000 and 4,000 psig, and we found that the condensed water would be 220. We did that together, right? After we know the amount of water, we use Hammerschmidt equation to calculate the percentage of inhibitor that should be in water phase. Okay, water phase. We found that it is 11%. We know the temperature that we want to do the shift of the curve from headed graph, right? This graph. Okay. This one suggests 74. So we have flowing temperature of 68. Okay, that's a flowing temperature. And we know that from the hydrate curve, at pressure of 4,000 on the operating pressure, hydrate form at 74. So we want to move from 74 to 65, right? 74 minus 65 is 9. We put 9 into Hammerschmidt equation. Everyone get the release form? Who haven't got it? One here. Marshall, please count the number of people and the number of letter that you get, okay? So after we substitute the value, we get W. W tells us the rate percent of the inhibitor that should be in water phase, okay? And then we try to use this graph to find out how much is in the gas phase. I find another one from Gas Association, this curve, okay? This one comes from Arnold Stewart. I checked with the Gas Association, what's the name? GPSA. Okay, I checked with GPSA. What you need to do is the correction over here. That is not 80, that is 60. Okay, and that is 65. Okay, GPSA say 60 and 65. Arnold Stewart took it from GPSA, okay, and they make some typo. And that is not 0.9, it's 0.8. Okay, that is it, 0.8. So in GPSA, that line is 60 and that line is 65. This graph is to find how much should be methanol in gas phase. Okay, how much should be methanol in gas phase? So we know that we have 4,065, right? At 4,065, you will have about 1.52. Okay, 1.52 is the ratio of power of methanol in gas phase, okay, per million standard cubic foot of gas, and that standard is 14.7 and 60F. Okay, ratio of methanol vapor. So this graph tells us how much methanol go in gas phase. For methanol that go into oil phase or hydrocarbon phase, we just assume 0.5%. Okay, and 0.5%, it is quite a lot. Okay, 0.5%. You remember this one? That's my 0.5%. Okay, 0.5% dissolved in oil. Okay, so we have oil specific gravity of 0.86, and we have for that 0.86 is 300 pound per barrel. So 0.5% of 300 pound per barrel is, and we have 60 barrel per million standard cubic foot, right? That is how much it produces. So that 0.5% equal to 90 pounds of methanol. All right. What I want you to focus here is this number, 24, which is the one in water phase. 11, so we have about half lost as a vapor in gas phase. And we have 90, the majority part going to oil, which doesn't do us any good. Okay, so when we add methanol into this gas system, we have to add 125 pounds per million standard cubic foot. When we add 125, 24 is a usable one that go to water phase, okay? And 11 will go into gas phase, and 90 is a loss in hydrocarbon phase. You got this? So even though you need just 24, but you need like 5 times more than the actual value, right? Instead of adding 24, you add 125. So the assumption in this calculation is that the phase equilibrium occur everywhere. Okay, so whenever we add it in, it distributes in gas phase, distribute in liquid phase, and go to water phase, like what we assume. So we assume, okay, first it go to water phase 11%, then it have some part going to vapor phase, and have 0.5% going to liquid phase. So this is a rough calculation. So the chemical company may suggest, what do they suggest? Double the amount and buy that from them. So if you double the amount and buy that from them, it will work for sure. Right? Okay, that's you pay double too. All right. So basically, this number shows you that you need a lot of methanol per million standard cubic foot, okay, that we produce. That's for Hammerschmidt. So about 125 is needed, just 25% dissolved in water. Loss in oil phase is significant in general. Okay, the volume of methanol is about, okay, do some calculation, 125 pounds per million standard cubic foot divided by 0.8 multiplied by 8.33, so 18 gallon per million standard cubic foot. So 18 gallon of methanol is impractical. The better solution is to separate the condensate first before add the methanol, if possible. Okay, if possible. And now you know how to do this, right? I show you, first method is show you with this kind of graph. You remember this graph? Another method is to use a graph in the back, this one, and I get 1.52. If I use 1.52, instead of 11, I get 16.7 pounds per million standard cubic foot that go to vapor phase. But if you get 11, early on we get 11, right? 11 pounds in vapor phase. If we use a better graph, we get 16 pounds. This part is not the majority of the loss. The majority of the loss is going to oil phase. Okay. All right. No question, right? You will have homework about this, and because we explain it a lot, so you should be able to do it. And another homework that you should expect is like this may not be in the homework. Just put in a quiz or exam or something. Okay. Good. You should be able to do it anyway. I cover it. Okay, let's do something else. We know about the hydrate, right? Next is about separator. for this lecture, I will try to cover as much as we can. For the separator, you have seen some phenomena in the lab, and lecture we talk about it more in detail. So you may remember this diagram, right? For high pressure or high temperature well, low temperature well. So low temperature well we have line heater. High temperature well we may have to cool it before do the gas treating. Okay. So the part that we talk today is about this one, high pressure separation, or you can have lower pressure separation. Okay. So gas liquid separation is in this lecture, and oil water will be next time. Okay. The dissolved gas come out as a pressure drop. You remember the phase diagram? Look like this when pressure, look like that. When pressure drop, then gas come out. Okay. So we have gas in liquid phase. Gas carries some liquid droplet. Okay. Liquid phase can have some gas bubble, and we want to separate them from each other. Okay. For pump need gas-free liquid. No gas in the pump and no liquid in the compressor. Okay, no liquid in the compressor. And basic sediment and water should be less than 1%. Right? Gas should not be more than 7 pounds of vapor, water vapor per million standard cubic foot. Right? We learned that from the gas contract. Separation vessel is normally the initial process in the facility. So if we do it incorrectly, it will be a bottleneck and reduce the capacity of the entire facility. So it is important, right? Separator is the first step. If we don't do it right, it will be a bottleneck, and we don't want that. Two-phase separator separate gas from liquid. Okay, three-phase separator can separate liquid stream into crude oil and water too. So we get crude oil and water. Name of separator, sometimes they call gas scrubber. So this is for high ratio of gas to water flow rate. Sometimes we call slug catcher. Okay, that is a two-phase separator. It's for a large gas capacity with liquid slug. Okay, so sometimes they call traps. Okay, separator that handle flow directly from the well. So you may call gas scrubber or slug catcher or something, but basically it is a separator. Okay. For three-phase, we have free water knockout. It is a three-phase separation. We will talk about it later. For oil layer, water layer, how do we get free water from free water knockout? Okay. Factor affecting the separation. In the exam, you will have to be able to tell some of these, not all. Okay. Number one, gas and liquid flow rate. If we have gas and liquid coming fast, we need a bigger separator. Okay. Operating and design pressure and temperature. If it is hot, we may be able to separate it easier than when it is cold, because when it is cold, it has higher viscosity, right? And pressure, if it is a high pressure, we have to buy a high pressure unit, and pressure can cause gas to come out of solution and create bubble, create foam too. Okay. The next part that we have to consider when we design the separator is surging or slugging tendency in the feed stream. So slug is a pocket of liquid that usually we don't have, but sometimes it comes in the large quantity. Let's say we have a long transmission pipeline. From time to time, maybe one time in a month, they pick it, put a sphere peak here. So this peak just look like a spherical shape, like a ball, big one. Put it in the pipeline, gas behind it, push this ball ahead, right? and this ball remove any condensate or any liquid that accumulate on the pipeline. Like push everything ahead of it. So it will go to processing facility, gas processing facility. This is a little bit of liquid accumulate over a long pipeline distance. So at the end it will be a lot come one time. So processing facility will need to have a slug catcher. Slug catcher is just to separate gas from liquid. Okay, you will see a big one in Oxy Sundown. It's very big. In the front, in the very front. It is the first unit that get gas from a transmission pipeline. Next part is degree of separation. So this is the part that we have to consider. Do we want to remove 100% of particle greater than 10 micron? Is that what we want to do, or do we want to go down to 1 micron or something? So what size is okay? What size of liquid droplet is not okay? So this part will impact how we design the separator. And presence of the impurity. Do you have impurity? If you have sand, scale, paraffin, it may cause more problem on emulsion, for example. And we have to look at foaming tendency of the crude. If we have foam, we have foam breaker, or we have add some plate into the facility to break any foam. And we have to consider the corrosive tendency of liquid or gas. What kind of material that compatible, or we expect that, okay, after a certain number of years, we have to change separator or something. So, okay, let's take a look at separator. You have seen this in the field trip, right? And we have the new version of picture has a pressure relief valve, so I added here. Pressure relief valve inside, there's a spring. Okay, when pressure is greater than the spring constant, it come out. So when you go to fasting battery, we smell something that's come from some kind of that valve, maybe another valve, not this relief valve, but another kind of valve that relieve gas too. We have a mist extractor on the top, pressure control valve, and in the lab, I told you, right, pressure relief valve has to be put on the location that it can sense the pressure build up. So if you have paraffin can plug this part, plug the mist extractor. When it plug the mist extractor, gas coming in but cannot go out. So it's build up the pressure. It will break the weak spot. So if we have pressure relief valve, it will not break the separator. It just come out from there. So if I ask you, do we install it over here or over here? You have to tell me the right location, okay? It has to sense the build up of the pressure in the case of mist extractor get plugged. Inlet diverter, this part, liquid collection section, the part that collect liquid, okay? Gas liquid interface, dump valve, okay, or level control valve, gravity settling section, that section, and we will talk about each section separately. This one is a horizontal one. For horizontal one, we also have mist extractor. We have pressure control valve, so that the pressure inside the separator is at a constant pressure. And we have inlet diverter, gravity settling section, liquid collection section, okay, level control valve. Four main component of separator. Which section is, what is the four main component? Number one, inlet diverter. Number two, gravity settling section. Number three, liquid collection section. Number four, mist extractor. So you know how to answer it in the exam, right? I asked you, what is the four main component of the separator? Your answer is four of that. Of course, if it is in the open book, you just open the book and you answer it. If it is in a closed book, you memorize that. I haven't made the exam yet, so I don't know whether closed book or open book. Who missed the class? Ernest Munoz. He took my book too, not just Mr. Class. Nicholas Longcar. Just two people, okay. Right. Inlet diverter. It is where 80-90% of separation happen. Okay. Liquid and gas come at different momentum. So if they have the same speed, the one that have higher density has a higher momentum, right? It has different momentum. So when it hits the plate, liquid will actually hit the plate, but gas maybe just move around. It not really hit the plate, okay? It have less momentum, so it may not be able to penetrate the layer of liquid and reach the plate. So if you add the plate there, the one that have higher momentum can hit the plate and fall down, and gas just move around. Good? So that is inlet diverter. So it divert the direction of fluid. If we don't have the inlet diverter, it go here and it splash and maybe go there and go there, right? Gas may splash or something. Horizontal separator is even worse. If we don't have inlet diverter, what do you think? It just come in and shoot as a jet and go to mist extractor and flood the mist extractor right away. So we need inlet diverter, right? Okay. So it's the separation based on their momentum. Very important section, okay? Because the most separation happen over there. Next part is gravity settling section. Okay. Gravity settling section. The top part, right? That's gravity settling section. Small liquid droplets in gas separated out by gravity and fall into gas-liquid interface. This section is sized so that liquid droplet greater than 100 micron fall down. Okay, fall down like that. You see, the drop just go down. See that picture? If we have the separator that is very thin, or we have more liquid level. So if my liquid level, instead of that much, I have almost full. Okay, I have almost full. And I have the same volumetric flow rate of gas coming in. This means gas will flow very fast in that gap, right? Gas will flow very fast in that gap. So liquid droplet may just stay in gas phase and go out on the top. We don't want that, right? Okay. So the main function of gravity settling section is to remove liquid droplet from gas. So if we don't do that properly, the separator is too short, too thin, too high liquid level. Droplet greater than 100 micron can overload the mist extractor, and the mist extractor doesn't work as it should. The mist extractor should extract just the mist, not the big droplet, okay? Just 100 and below. Liquid collection section is at the bottom of vessel. So if I give you this picture and put the four main section of the separator, you have to know that, okay, that part is a liquid collection. Of course, for the one in the lab has oil bucket, water bucket. You still remember that? So liquid collection part, it provides the retention time needed for any entrant gas in the liquid to escape through the gravity section. We didn't really talk about the retention time. Okay, retention time is the amount of time that fluid particle stay in the separator. Okay, make sense to you? If the separator is small, so we flow a lot. When it enter and a little bit, then it reach the outlet. So we don't have enough retention time, right? If the separator is big, when it go inside, it moves slowly, so it stays longer in the separator. So it have longer time for the separation. That is the retention time. Okay. So liquid collection section can provide a surge volume to handle intermittent slug. Horizontal separator can handle slug a little bit, but not as good as the vertical separator. What is the surge? Let's take a look at this. Okay, let's say we have a pocket of liquid, high quantity, come at one time. What happens in the vertical separator is the liquid level go up, right? A little bit. And it is fine, no problem. Okay. What happens if we have a separator? Okay, mist extractor maybe over here and outlet over there. So liquid level, so when we have the surge come, liquid level go up a little bit too, but it may flood the mist extractor or make droplet go out. So the level change is not good for horizontal separator because the same amount of the change in the level can cause problem, right? It prevents the separation. But in the vertical separator, the change in the level is still okay. See this? And more, but if we have too much, vertical separator cannot do anything anymore because it will be completely filled with liquid. Okay, and in the slug catcher, I see just horizontal slug catcher. I didn't see vertical slug catcher, and one of the main reasons is if we, okay, let's take a look at slug catcher a little bit. You see this? The volume has to be that big. Okay, if you put that and stand it up, it may be too tall, so they have to put it horizontally. Just that. Okay, main component. Retention time is affected by the amount of liquid in the separator. We talk about this, right? If we have more or high liquid level in the horizontal separator, so high liquid level in the horizontal separator, just the top part, not much cross-section area is for gas to flow, right? Not much gas cross-section area. So this means gas will flow pretty fast. If we lowering the liquid level, so there will be more cross-section area for gas to flow. So if we have the same volumetric flow rate coming in, it flows slower. The speed will be slower, correct? So you may estimate the retention time by available volume based on the available volume and the volumetric flow rate that's coming in. So if we have 10 cubic foot available and it's coming in at 1 cubic foot per second, so it will stay inside roughly 10 seconds, right? So it's 10 divided by 1. So if we have 100 cubic foot available, it comes in at what? 1 mmSCF D. You can do the calculation, right, to get roughly the retention time. So you need to be able to do a little bit of unit conversion. Good? Of course, you have to be able to do that. So that's about liquid. If the liquid level is too low, so we don't have much retention time for liquid, but we have more retention time for gas. Make sense? If the liquid level is low, the cross-section area for liquid to flow will be less. Okay, so more volume for gas, this means it holds more gas. So gas stay inside longer, right? If you have more volume for liquid, then liquid stay inside longer. So for horizontal separator, the change in the liquid level, it impacts both gas and liquid retention time. So if we increase the level, Retention time for gas will go down, but retention time for liquid go up. Okay, if we reduce the liquid level, retention time for gas go up, but liquid will go down. Make sense to you? Alright. Mist extractor section, or you may call coalescing section, it used to coalesce any mist that hit the mist extractor. It provides large amount of surface area for coalescence to occur. Once it's coalesced, it forms a bigger droplet, then it fall down. Okay, it hit the mist extractor, very like 12 micron droplet hit the mist extractor. Many of them come, so it coalesces and then fall down to liquid oil bucket or liquid collection section. Liquid droplet cannot flow. The rapid changes in the flow direction because of mist extractor. Instead of mist move straight, it cannot go straight, right? It has to go into zigzag direction. It cannot go straight. So it increases the distance for vapor to travel. So it has more time to separate too. And the droplet that impinge or coalesce will fall down. We will talk more about that. Good. So you know about four main components of the separator. Cotton wood. What do we do with mist extractor? Main function of mist extractor.
Use large particles out of the gas.
It mist extractor do what? Remove.
Large particles from the gas.
Remove mist. Right? Oh, okay, very good. So next one, Alexandra Wascom. Hi, Alexandra. What about liquid collection section? What do we do with that? It's to collect the liquid. Okay. So if we have a large liquid collection section, is that will provide more retention time for liquid or less retention time? More volume for liquid collection section. If we have more volume for liquid collection section, will provide more retention time or less retention time for liquid phase? More or less? More. Okay, good. Yeah. So it is bigger, so it stays inside longer, just like that. All right. So I think we talked about this in the lab a little bit. Liquid come, hit the inlet diverter, cause sudden change in the momentum, and there is a separation. Initial separation occurs at the inlet diverter. Gravity causes the liquid droplet to fall down, fall into gas stream, fall out from gas stream. Liquid leaves through liquid dump valve. Dump valve is regulated by liquid level controller. And gas and liquid mist flow. Gas and oil mist flow over the diverter and go into gravity settling section and go to the outlet. Mist extractor extract in the mist. That's just how it works. Very easy, right? Okay. Do you still remember input, control, and output that we learned from the field trip? So the sensor will be the input part, and the control will control whether the valve should open or close, and the output is the part that do the action. You remember that? So we don't have to talk about it anymore. Okay. Working principle for the vertical separator, it is the same as the horizontal separator. Very good, right? Solid phase collected at the bottom. So in the vertical separator, at the bottom, we have a cone shape to collect any sand particle or any solid particle at one location, and then we can drain it. Okay. Spherical separator, we don't use it anymore. Done, right? That's a spherical separator. The shape is sphere, so sphere shape can hold or can withstand a higher pressure That's a good thing with spherical separator. So the working principle is the same as horizontal separator. We didn't use much in the field. Difficult to operate, difficult to get the right size. It limited surge capacity. It can withstand the higher pressure, but it's difficult to make. Fabrication difficulty. Look at this. We have gas and oil inlet coming from the top. It hit with the inlet diverter, so liquid phase will hit, but gas phase will move around, right? So when it hits, liquid will fall down into liquid collection section. Gas that have some liquid droplet inside go into this section, gravity settling. So from this gravity settling, liquid droplet will come out from the gas phase. It go through the mist extractor, extract any mist that left behind, and then we go to gas outlet at the bottom, and we have liquid outlet at bottom too. That is what is happening inside. But we don't use that much. What you will see is just vertical or horizontal. Okay, separator construction. Regardless of the type of separator, we need the following. Number one, inlet diverter, okay, to change the flow direction. 90% of separation is happening over there, 90%, okay? And we need a droplet separation section or gravity settling section. So 100 to 400 micron should be removed from that section, fall down from gas. Liquid collection section allow the equilibrium. So we should have enough time for any gas that stay in liquid phase to come out, okay? And we have mist extractor to extract 110 to 100 micron. So in reality, okay, this is a note from Watson that we don't know the particle size distribution. The particle size is not just one side, but it is a distribution. So the capacity of separator is difficult to say. So we should use the mist extractor every time. Just add the mist extractor. Done. If you don't have mist extractor, not good. So vertical separator, we have relief valve. So relief valve, that's why we talk about this. In the new version, they move the relief valve from here to the side. Don't put it over there. Not good, because that is after mist extractor. Okay? If mist extractor get cracked, that relief valve won't feel anything. Don't put it over there. So the advantage of the separator is small footprint. Doesn't require much area. So they like to put it on the subsea platform. Less chance of liquid entrainment. Okay, so we have just gas, have some liquid go up, right? And liquid go down. So we should not have any liquid in gas stream or gas in any liquid stream. So it's good. It can handle the surge, and absolute level does not affect the separation efficiency much. Look at the liquid level. So if we have the separator that look like this, we have at the inlet like that. So if we have liquid level that is at the bottom, what is the gas speed? Go up to the top. So the gas speed will be the volumetric flow rate divided by area. Area will be that cross-sectional area, right? That is that cross-sectional area. So volumetric flow rate divided by cross-sectional area will be the speed of the mist that move up, right? If you have liquid level instead of 20%, maybe 40% higher, what happened? The cross-section area is the same. It doesn't change the cross-section area of the flow of the mist. It is still the same. Okay? Of course, if you have the liquid level too high like that, you are going to have the problem. The liquid level should be lower than the inlet. Otherwise, we like try to push bubble through the liquid and we form foam or something. So it doesn't impact much. Alright? But horizontal separator, the liquid level directly impact the area of the flow. So if the liquid level go up, the area of the flow for gas reduce. Gas flow faster, we have lower retention time. Okay? And vertical separator good at the solid phase too. Disadvantage, okay? It has small interface area for liquid-liquid separation. So in horizontal separator, the surface area is that much, right? More surface area. In vertical separator, the surface area will be just that. So the surface area for liquid-liquid separation is less, okay? And you need ladder to access it. And if you put it on skid, I don't think you really can put it on skid and move it, okay? For horizontal one, they said we can put it on skid and just move it. So you put it on skid, okay? So that's a skid. And we move the whole thing vertically. So you have a truck, right? And the separator like this. So what happens if you go into some Y on the top, or you have to go underneath the highway or something? Crash. So we have to lay it down. Horizontal separator. Okay, look at the location of the relief valve. Over there is good because if the mist extractor get plugged, it will sense the signal, right? So it have a smaller diameter for the same gas capacity. Okay, smaller diameter for the same gas capacity. So you have more. What's a smaller diameter? I'll check on that part. You have any comment on that small diameter? Oh, okay. The horizontal separator can be long, right? And it doesn't need to be that fat. Okay. And it has large interface area for liquid-liquid separation, gas-liquid separation. It can handle foam very good. It's good at handling foam handling. So we have foam eliminator over there, so it can remove foam. Okay. Vertical separator, not quite at doing anything with foam. Okay. Easy to hook up service and skid mount. We can put it on the skid, move it, not a problem. Okay. And if we have a lot of area, we just put it there. In the yes question.
Why is it smaller diameter
I don't know. But what?
Just less steel.
Oh. Yes, of course. It's less steel and less cost. Okay. Okay. Small diameter can withstand more pressure. There's an example on the separator. So it has less liquid surge capacity and it's not quite good at handling solid. Okay. It's slower response to level control. Absolute level is critical to separation efficiency. What does it mean? Absolute level. So when liquid level is too high, gas cross-section area is slower, so gas move fast, right? So in the vertical separator, the liquid level doesn't change the velocity much, just that. So it can handle solid, okay? Horizontal separator can handle solid, but we have to do something more. I will talk about that. So horizontal versus vertical separator. So for process, horizontal better, gas liquid has more area to reach equilibrium. Okay, so if we have some kind of foam, we have a lot of area for the foam. Or if we have a oil water emulsion, we have more surface area for it to separate, and it will reach the equilibrium for the oil and gas phase, right? It have more surface area. Solid, if you have solid, the vertical part is better. So vertical separator requires small footprint, small area. Vertical is better for liquid surge access. Horizontal is better, don't need to climb that high. Ease of shipment, horizontal is better if it's vessel, but for vertical we can just lay it down and ship it too. Okay. Working principle for another kind of separator. You don't see this in the field. Okay. This one is centrifugal type, centrifugal separator. I just want you to be aware of that there's something else too. It's not just those two types or three types with spherical. We still have centrifugal separator. Some people call it cylindrical cyclone separator, CCS. Okay, so it uses centrifugal force to enhance the separation. We have angle inlet, liquid come in and then rotate. Okay, centrifugal force can be 5 to 2,500 times of the gravitational force in a small high pressure unit. So it has more G for the separation. Okay, flow pattern is double vortex. Gas move spiraling downward along the wall and upward in the center. So it's rotate around the wall and then move out at the middle. Spiral velocity in the separator can be several times higher than inlet velocity. So we make it move faster. Use the centrifugal force to do the separation. Liquid impinge on the wall due to radial velocity. Okay. Cylindrical cyclone separator designed to handle liquid flow